Now we've talked about two different types of mechanical waves, but what we haven't yet talked about is what happens when waves meet. How do they interact? If I have a string and I send a wave pulse from each end, what happens when they meet in the center? Now, if they have two pulses of the same sign, is that any different from what happens if we have two pulses of opposite sign? So, to start with, let's have a look at that simple case and see what happens when we send wave pulses along a string. So what we're going to show here are what happens when two pulses on a string come together. So for the string, we've got this dense metal spring which has a high mass per unit length, so that the speed of the pulses is not going to be exceptionally high. Now what we're going to do to start with is we're going to send two pulses with the same sign along the string. So look closely to see what happens. So what you should have seen is that when the pulses came together, their amplitudes added, and so that right in the center when the pulses met, we had a very large amplitude, or twice the amplitude of the individual pulses. Now look again, and we'll do it another couple of times so you can confirm that you see these two pulses adding together and then passing through each other and carrying on. So that shows two pulses of the same sign. What we're going to do now is show two pulses with opposite signs. So you'll see one pulse which comes with an amplitude to one side of the string, the other pulse will come in with an amplitude to the opposite side, and let's see what happens when they meet. So what you should have seen there is that the two pulses pass through one another. They don't meet and cancel out and stop, but when they do meet in the center, the string almost returns to its equilibrium position. That won't be precise in this case because the two pulses that we're generating are not identical, so there won't be a perfect cancellation for that brief instance in the center, but there should be a pretty good cancellation. So we'll try that another couple of times. So look for the cancellation in the center and look for the pulses passing through one another. So what we demonstrated there with the string is called the principle of superposition. When you place two waves on top of one another, the displacements add, and the net displacement is the sum of the displacements from the individual waves. So to understand the maths behind that, let's have a more detailed look at the wave equation. So here's what we saw with the string. We saw two pulses, each moving in towards one another, and as they passed through one another, we saw this large amplitude pulse briefly in the middle. So what's going on here? Well, here's our wave equation that we're familiar with, and let's assume that we've got two solutions to it. One here which we'll call phi1, and one that we'll call phi2. So these are both solutions to our wave equation here. So what we want to know is what happens if we add these two solutions. So if we add them together, then we're going to have phi1 plus phi2. So is this a solution as well? right? Is this a solution to our wave equation as well? Because if it is, then of course what we can do, we can always add solutions of the wave equation to get other solutions of the wave equation, which would explain what's going on here, that the sum of these two displacements gives us a third solution to the wave equation. So let's have a look at this. Well, we've got partial squared and now phi1 plus phi2 by partial x squared. Well, that I can separate out, and I can say that's partial squared phi1 by partial x squared plus partial squared phi2 by partial x squared. But each of these, we've said, are independently solutions to the wave equation. So I can take this expression here and I can substitute it into the wave equation now just using phi1, and what I find is that this is going to be equal to 1 over c squared, and now I've got partial squared phi1 by partial t squared, and here I'm going to have the same thing. I'm going to substitute that into the equation here, and I'm going to get partial squared phi2 by partial t squared with a 1 over c squared out here. Well, now I can just factor this. This is 1 over c squared, and then it's going to be partial squared, and I can combine these together, phi1 plus phi2 divided by partial t squared. So what I've shown here is that if phi1 and phi2 are independently solutions to the wave equation, then the sum of the two of them is also a solution to the wave equation, and that's why we can just add the two displacements together, because the sum of these two independent solutions is also a solution to our wave equation. And the reason for that is that the wave equation is what we call a linear equation. It has second order differentials in it, but you don't have terms like this squared, right? That would be a nonlinear equation. It's only to the power 1, so it's a linear equation, and that means that if you have two solutions to it, then the sum of those two solutions is also a solution to the wave equation, and that is why superposition, this principle of superposition, where we can add the displacements together, that's why it works. So now that we've shown that we can just add two waves together, what we've got here is a simulation of two pulses going along the string. So we're simulating what we showed before. On the top you can see two same sign pulses coming in from either end, and as they pass through one another you can see that you end up with a single very large amplitude pulse in the center that then separates and the two pulses pass through one another. On the bottom we have two opposite sign pulses, and again the pulses pass through one another. The difference is that when they merge in the center, instantaneously the string will go to a zero displacement flat string. However, it's not stationary, it's still moving at that point, and so the moves through the equilibrium position and out the other side, and you end up with the two pulses separating again, which is exactly what we saw with the string demonstration. So we've now seen what happens when two waves are superimposed on top of one another. This is the principle of superposition, and we've seen that the displacements of the two waves just add together to give us the net displacement for the medium. So next we're going to ask what happens when a wave comes to the edge of its medium. If I send a wave down this wave machine, what happens when it comes to the end of it? It can no longer carry on propagating because there's no more wave machine. So what happens there? And we're going to discuss and derive what happens by considering the conditions that must apply at this boundary. And we're going to introduce two types of boundary: a so-called closed or clamped boundary where we hold the boundary fixed so that there can be no displacement, and an open boundary where the medium is free to oscillate as much as it likes.
So what we're seeing here is a wave that's coming in and it's hitting the edge of its medium here, and this is a clamped boundary for this medium. So what that means is that the displacement here must be zero always. Now if we look at the wave that's coming in, we'll call the displacement due to this wave the incident wave, so we'll call that phi I, and then of course we have a reflected wave here and we'll call the displacement due to that wave phi R. Then our boundary condition is that the sum of the incident wave plus the reflected wave must be equal to 0. If the boundary here is x0, then we'll say when x is equal to x0. So if we look at this, what we've got is we've got a cosine wave here, and we've got a cosine wave here if we look at the wave solutions in the trig form. And the only way these are always going to be zero at this position here is if the phase difference between them, so we have a phase difference between these waves, if the phase difference at x equals x naught is equal to pi, right? So this is a phase difference at x is equal to x naught. So what that means is that we have to invert the phase of the reflected wave. So this reflected wave has the opposite phase to the incident wave to ensure that this boundary here remains with a zero displacement at all times. Now, of course, since this wave is propagating in the opposite direction, the fact that you have perfect cancellation here at the boundary does not mean that you will always have perfect cancellation elsewhere. And so what you see here is that you do indeed get a displacement that's not zero as you move away from the boundary. It will momentarily go to zero as the two waves, as you hit the midpoint of this wave pulse, where you get precise cancellation here and all the way along here as well. And then as this wave carries on moving in this direction and this wave moves in the opposite direction, then of course you'll end up with a pulse, but now the pulse will be negative as the reflected wave dominates, and you end up with the final state where you end up with a negative inverted wave pulse going in the opposite direction. Now, if you have a continuous wave, this is what you have on this side. So this shows a continuous wave coming into the boundary and reflecting off it. And so you still get a wave, but now what happens is the wave amplitude oscillates up and down. You had a large amplitude here, and then you always, momentarily it will cancel. And these points here, you will see that you always got a zero amplitude at these points. And we'll discuss that in a little bit more detail when we move on to standing waves. So here we can see an animation of the diagram that we were looking at before. What we've got on the top is we have a single wave pulse that's incident on a closed boundary at the right-hand side of the screen. And as you can see, as this pulse reflects, its phase inverts and we have a negative going pulse that comes back in the opposite direction, and the displacement at the boundary is always zero. On the bottom you can see a continuous wave that is coming in from the left and reflecting off the closed boundary on the right. And what you see is that the displacement of the medium is zero at the boundary, but also zero at several other points close to the boundary. And in between these points of zero displacement, the amplitude of the medium is twice the amplitude of either the incident or the reflected wave. So this is showing you what we expect to see for reflection at a closed boundary. Let's go and actually look at a real physical system using the wave machine and see if this is what we actually observe.
So we've seen now how the boundary conditions at the edge of a medium require the incident wave to be reflected, and that wave will have to undergo a phase change if it's at a closed boundary. Now, we already knew, in fact, that waves were reflected at boundaries. If you've ever heard the echo bouncing off a wall, then that's an example of a wave that's reflecting at a closed boundary. Although, of course, you wouldn't be aware that the phase had changed by pi. So, to show you that there is a phase change of pi, what we've got here is this wave machine. And what we've done at the far end is clamped the last rod. So the final rod at the other end of the wave machine cannot move. And I'm going to send a wave pulse down here, and I'm going to send an upwards wave pulse, and look at what happens when it hits the far end of the wave machine. And so you can see there that the pulse was reflected and the sign of the pulse changed. It underwent a phase change of exactly pi. So let's try that one more time just to show you. And this time, in fact, what I will also do is I will hold this end of the wave machine. So this end of the wave machine will be clamped as well. So what you should see happening is it'll reflect at the end and change its phase, and then when it hits this end, it'll also reflect and change its phase. Though, of course, because of friction in this machine, the amplitude will be decreasing all the time. So let's give that a go. And so there you can see that each time it reflects at the end, the phase changes, and of course now it gets a little bit chaotic. But you could see that the pulse inverts. So let's try that again if I remove this clamp, and we'll see what happens at an open boundary.
So what we've got here is we've got another wave pulse, and it's coming into the boundary, the edge of its medium here. But this is now what we call an open boundary. We're not constraining the displacement to be 0 anymore. So if you want to think of this in terms of a string, you can think of it that we've got a frictionless pole here, and we've got a loop attached to it, and then the string is attached to that loop. So it's free to move in an upwards and downwards direction, but it cannot move in the longitudinal direction. So it's got free movement here, and there's no friction. So what this means is that there cannot be any angle to the string at this point, because if there was an angle, if you imagine the loop here and you had the string acting down at an angle, that would generate a net force down on the loop, and since it's a frictionless and we're assuming the loop is also massless, that would immediately cause the loop to move with an infinite acceleration if we're taking a massless loop until the string was horizontal again. So our boundary condition here is not that the displacement is 0, right? The displacement is clearly not going to be 0. Instead, it's that the rate of change, the gradient of the string, the rate of change of displacement with respect to x is 0. So it's partial phi by partial x is 0. And that's our boundary condition at an open boundary. Now, to get that condition, what we need to do is we need to invert the slope of the wave. But inverting the slope of the wave means that we want to have the same phase as the incoming wave. So now, if we have our incident wave and our returning wave, so this is our reflected wave here, phi r, then what we have is we have a phase difference between the two of them of 0. And that's so that the slopes at this point will always cancel, because remember, our net displacement here is going to be the sum of phi I plus phi r, and so our slope at this point here is going to be the sum of the two slopes plus phi r. And these two slopes are going to add to give 0 if all we've done is reflect the wave, right? Because now we've got the same wave going in the opposite direction, and so it has the opposite slope. So we have a 0 phase change here. And if we look at a continuous wave reflecting at a boundary instead of a wave pulse like we had on the other side, then again what we're going to see is we see that we end up with areas with a large amplitude oscillation, and then we end up with these points here where you end up with a 0 displacement at all times. The difference being is that now we have a large amplitude oscillation at the boundary itself. So this is one of the points where you get a maximum oscillation amplitude, whereas before with the clamped boundary here we had the 0 oscillation amplitude. And we'll come back to this when we deal with standing waves. So here we have the same diagram we were just looking at, but now we've animated it. Now, on the top you can see a wave pulse that's coming in from the left, and it's impacting this open boundary now on the right. And you can see the behavior is very different from the closed boundary case. For a start, we have a very large displacement of the medium at the boundary, but as you can see, the medium remains level. There's no slope at the boundary. The slope is 0 where the medium attaches to the boundary. The other thing to note, of course, is that the reflected pulse now is also of the same phase as the incident pulse. In other words, it has a positive displacement. It's just moving in the opposite direction after it reflects. On the bottom, you can see the same boundary now reflecting a continuous wave. So there is a blue wave coming in from the left. It's impacting the boundary on the right, and then we have the reflected wave shown in green that's moving off in the opposite direction back to the left. And as you can see at the boundary, the two waves are having the same phase. There's no phase change at the boundary as there was for the open wave, and the result is now is that the displacement at the boundary is very large, and in fact grows to twice the amplitude of the incident wave. However, just like the case of the closed boundary, there are still points near the boundary where there is zero displacement. The difference is now is that the zero displacement point is not at the boundary as it was for the closed boundary case. It's now a maximum amplitude point that is at the open boundary. So now we've seen the computer model, let's go and have a look at the wave machine again and see what happens for a real wave.
So now we've got the same wave machine, but the clamp at the far end has been removed, and so now the far end is an open boundary. Now I have to be a little bit careful when I do this, because as we saw when we were doing the maths, the amplitude you get at the far end is the sum of both the incident wave and the reflected wave, which means that this final bar will have twice the amplitude of the incoming wave. And so I have to give it a small amplitude here, otherwise the bar will tilt too much, whack into the base of the machine, and then you won't see the phenomenon you're expecting. So here goes with a small incident pulse, and you should see it reflect, but now we're expecting to see it without a phase change. And you can see there it reflected without a change of phase. I had a positive pulse going in and a positive pulse coming back. Just to verify this, I'll actually send a downwards going pulse now, and you should see it come back as a downward going pulse. And there we go. So in fact what I'll do now is I'll do the same as I did for the clamped end. I'll leave this end free, and you should see the pulse reflect backwards and forwards, but it will remain a downward going pulse because both boundaries now are open boundaries. Okay, so it got a little bit chaotic there, but hopefully you could see that it did reflect without a phase change. So we've seen now that when a wave reflects at a boundary, the phase of the wave can change or may not change depending on the conditions at the boundary, but in either case it's certainly reflected and then superimposed over the incident wave that's hitting the boundary. So when we do that, we're going to be combining waves with different phases. So let's have a look at what it means for the two extreme cases where we add waves either perfectly out of phase or perfectly in phase.
So when we're adding waves together, we need to consider whether they're in phase or out of phase or somewhere in between the two. So what we've got here is we've got two waves, we'll call this one wave 1 and wave 2, with different amplitudes, right? So the amplitude of 1 is not equal to the amplitude of 2. Now, if we have them out of phase, what that means is that you end up with a maximum in one wave corresponding to a minimum in the other wave, and so you end up with as good a cancellation as you can possibly get. And so you can see here that this deviation, when you've got them out of phase, this deviation here is going to be A1 minus A2, and we're taking the modulus of this because we don't know which one has got the larger amplitude. Well, obviously in this case, A1 has the larger amplitude, but the amplitude of the resulting wave is the modulus of the difference in the amplitudes, because clearly if we switched these round and gave A2 the larger amplitude, we'd still have this reduced amplitude wave that's the resultant of the sum of these two. So this is in the case where the phase difference between them is pi, which means that they exactly cancel, or well, they won't exactly cancel if they haven't got exactly the same amplitude, but you get the maximum cancellation. Now if you have them in phase, then there is a correlation between the maxima of each of these two waves. So again, if this is 1 and this is 2, then the result here is that this displacement is going to give us an amplitude of A1 plus A2. And so when we're in phase, then the maxima of both of these two waves occur at the same time and their amplitudes add together. Now if A1 is equal to A2, which is not the case here, then For the out of phase waves, you get that the net amplitude is 0, and you end up with perfect cancellation, and we just have a flat line through the center here. And here you'd end up with that the amplitude is equal to 2 times the amplitude of one of the waves, because they've got the same amplitude. So you'd end up with twice the amplitude. And if you've got a phase difference that's somewhere between 0 and pi, then of course you will end up with partial cancellation, not complete cancellation, nor will you end up with complete constructive interference. But these are the two extremes showing you how waves add together both in phase and out of phase.
So we've seen now what happens when we superimpose two waves one over each other, either from reflection at a boundary or from sending two pulses down a string. The next thing we want to look at is what happens when we have multiple sources of waves, and how do those waves superimpose over one another. And this gives rise to a phenomenon called interference, and that's what we'll look at in the next video.